48 years ago, we launched a spacecraft with less computing power than a modern calculator, and we gave it one job that sounded almost impossible: leave the solar system entirely. It did. And now, from 12 billion miles away, that same spacecraft just sent back a signal that has scientists quietly rewriting what they thought they knew about where our solar system actually ends. This isn't old data resurfacing. This isn't a glitch buried in an archive somewhere. This is happening right now, in real time, and the numbers coming back don't match anything researchers predicted. Here's what Voyager 2 found, why it caught NASA off guard, and why the answer might matter more to you than you'd expect. Let's start with the spacecraft itself, because you can't understand how strange this discovery is without understanding what it took to get here in the first place. Voyager 2 launched in August of 1977, just weeks before its twin, Voyager 1. Both were built for a single planetary tour that was only supposed to last 4 years. They were designed to take advantage of something that happens once every 176 years, a rare alignment of the outer planets that let a spacecraft slingshot from one world to the next using almost no fuel. Nobody expected either probe to survive past Neptune. Nobody expected them to still be transmitting data during our lifetimes, let alone decades after most of the engineers who built them retired. And yet, here we are. Voyager 2 is still out there, still listening, still talking back. It carries a golden record on its hull, actual etched instructions, sounds of Earth, greetings in dozens of languages, a message built for anyone or anything that might one day find it drifting through the dark. The record includes bird song, laughter, the sound of a heartbeat, and 90 minutes of music chosen to represent the full range of human culture, on the off chance that something, someday, out there, decides to press play. But long before it became a message in a bottle for the galaxy, it was simply the most productive spacecraft in the history of planetary science. It gave us our first close look at Uranus. It's still the only spacecraft to have ever visited Uranus, and the only one to have ever visited Neptune. It discovered active volcanoes on a moon of Jupiter, new rings around Uranus that nobody knew existed, and strange tilted magnetic fields on the ice giants that scientists are still trying to fully explain. Every single planet it passed handed back a surprise nobody had planned for. That pattern, as you'll see, hasn't stopped. By the time it finished its planetary tour, it had already outperformed every expectation NASA had for it. And then it kept going. For the next several decades, Voyager 2 pushed further and further from the Sun, past the orbit of Pluto, past the edges of anything we'd ever explored directly. It was heading somewhere no human-made object had gone before, the true boundary of our solar system. To understand why what just happened matters, you need to understand what that boundary actually is. Because it's not a line on a map, it's a battlefield. Our sun doesn't just sit quietly in the middle of everything, it's constantly exhaling, blasting a stream of charged particles outward in every direction at speeds over 1 million miles per hour. That stream is called the solar wind, and it inflates a massive bubble around our entire solar system called the heliosphere. Think of the heliosphere as an invisible force field. It's the reason we're shielded from a huge portion of the harsh radiation that fills the rest of the galaxy. But the galaxy pushes back. Out beyond the orbit of Pluto, the sun's wind finally runs out of strength and it slams into the thin, cold material that fills interstellar space. That collision zone is called the Heliopause, and crossing it means leaving the direct influence of our own star behind for good. Only 2 human-made objects have ever crossed that boundary. Voyager 1 did it first, in 2012. Voyager 2 followed 6 years later, in 2018. Both crossings made headlines at the time. Both were treated as a kind of finish line, the moment humanity officially left home. And when both crossings were compared side by side, scientists thought they'd finally cracked it. They thought they understood the shape, size, and behavior of the bubble that surrounds our entire solar system. They were wrong, or at least, they were only partly right. Voyager 2 is still transmitting even now, running on a power source that loses roughly 4 watts of usable energy every single year. Every scrap of data it beams back has to travel for over 19 hours before it reaches Earth, picked up by an antenna dish, built specifically to hear a signal weaker than a household light bulb. Which is exactly what makes the recent readings so strange, because something changed. Voyager 2's instruments detected a sudden sharp spike in cosmic ray density, far higher than anything recorded during its original crossing back in 2018. Cosmic rays are high-energy particles that originate from exploded stars elsewhere in the galaxy. Inside the heliosphere, the sun's magnetic field blocks most of them from ever reaching us. Outside it, in theory, they should hit at full, consistent force. A steady baseline, predictable. That's what the original crossing data showed. But this new spike wasn't steady. It surged, then it dropped, then it surged again, almost like the boundary itself was moving. Flexing, breathing almost, if a structure that large and that far away can be described that way. Here's why that single detail is such a big deal. For over a decade, the working scientific model treated the heliopause as a relatively stable boundary, something closer to a wall than a living structure. Voyager 2's newest readings suggest that idea might be incomplete. The heliopause might behave less like a wall and more like a shoreline, something that gets pushed and pulled, that expands and contracts over time, shaped by forces we never had the right instruments in the right place to measure before now. If that's true, then everything we thought we understood about the true size and shape of our own solar system needs a second look. Scientists actually have a name for this possibility. They call it heliospheric breathing, the idea that the bubble surrounding our solar system inflates and deflates depending on how active the sun currently is. The concept isn't brand new. It's been theorized since as far back as the 1990s, sitting quietly in academic papers as an interesting but unproven idea. The problem was always the same. No spacecraft had ever been positioned outside the boundary for long enough with working instruments to actually catch it happening in real time. Voyager 2 is in exactly that position right now, and the timing could not be more relevant. The sun is currently ramping up toward a period of higher activity in its long-term cycle. More solar activity means more pressure in the solar wind. More pressure in the solar wind means the heliosphere should, in theory, inflate, pushing the heliopause further outward, deeper into interstellar space than it's ever been measured before. If Voyager 2 really is recording that boundary shifting in real time, this isn't just an interesting data point. This is the first direct evidence ever recorded by a working spacecraft that the edge of our solar system responds to the sun in real time. Not simulated on a computer, not modeled from theory, measured directly from a location 12 billion miles from home. Think about what that actually changes. Every diagram of the solar system you've ever seen in a textbook ends with a neat, clean circle drawn around the sun's influence. That circle was always a simplification, a convenient way to draw something we didn't have enough data to describe accurately. Now, for the first time, we have a spacecraft on the outside, looking back, telling us the real shape is closer to a slow, pulsing bubble than a fixed, solid wall. And there's a second wrinkle in the data that makes this even stranger. The plasma density readings, essentially how tightly packed the interstellar gas is right around Voyager 2's current position, don't match the readings that Voyager 1 recorded at its own crossing point. That crossing happened 7 years earlier, in a completely different direction of space. And the numbers simply don't line up. That mismatch means the heliopause isn't just moving as a whole. It might not even be a uniform shape at all. It could be lumpy, uneven, thicker in some directions, thinner in others, depending entirely on what kind of interstellar material it happens to be pushing against on that particular side. We've only ever directly measured 2 points on this entire boundary, using 2 aging spacecraft pointed in 2 different directions. And those 2 points don't agree with each other. It's a little like trying to describe the shape of an entire ocean using only 2 buckets of water pulled from opposite shorelines. You'd learn something real, but you'd also realize almost immediately how much you still don't know. It raises an uncomfortable question for anyone who's ever looked at a tidy diagram of the solar system and assumed it was settled science. What else about that diagram is a simplification we've simply gotten used to treating as fact? It's not the first time a Voyager probe has caught the boundary doing something unexpected either. Back in 2012, right as Voyager 1 approached its own crossing, its instruments recorded something scientists nicknamed a pressure wave, a sudden compression in the surrounding plasma that rippled outward from an eruption on the sun months earlier. That single event let researchers calculate the density of interstellar space directly for the first time, simply by timing how fast the wave traveled. It was an accident of good timing that turned into one of the mission's most cited discoveries. There's also a quieter instrument on both spacecraft worth mentioning here, the plasma wave subsystem, essentially a sensitive antenna that can pick up vibrations in the charged particles surrounding the probe. When Voyager 1 first crossed into interstellar space, that instrument captured something that got turned into audio and shared publicly. A low, eerie hum that some described as the actual sound of interstellar space itself. It wasn't sound in the way we normally hear it. There's no air out there to carry it. But it was a real signal, translated into a frequency human ears could process, and it became one of the most unexpectedly emotional pieces of data either mission ever produced. That same instrument is part of what's now capturing this new cosmic ray spike on Voyager 2, feeding back a stream of readings that engineers on Earth are still working through, line by line, seeing what other patterns might be hiding inside it. And Voyager isn't the only mission that's ever tried to study this boundary. A separate spacecraft called IBEX, launched in 2008, has spent years mapping the heliosphere's edge from a much closer vantage point, using a completely different method, detecting particles that bounce back toward Earth after colliding with the boundary itself. IBEX's data has already hinted at a heliosphere that isn't perfectly round, showing signs of a longer comet-like tail trailing behind the solar system as it moves through the galaxy. Put Voyager 2's new readings next to IBEX's broader picture, and a strange, more complete image starts to form. A solar system with a boundary that isn't just uneven, but actively shifting shape as it moves. None of these missions were ever designed to work together this way. They were built decades apart, for different purposes, by different teams. And yet, piece by piece, they're assembling a picture no single mission could have captured alone. So why should any of this matter to someone who is never going to leave Earth, who will never see interstellar space with their own eyes? Because that boundary functions as our shield. Everything inside the heliosphere, every planet, every moon, every single one of us, is partially protected from the harshest radiation the galaxy has to offer. If that shield genuinely expands and contracts along with the sun's activity, then the level of cosmic radiation reaching Earth's orbit over the coming decades might not be nearly as steady as we've always assumed. That has very real practical implications. It matters for how satellites are shielded. It matters for how we plan long-duration spaceflight, especially for astronauts spending months or years outside Earth's own magnetic protection. It matters enormously for any future mission to Mars, where astronauts would spend the better part of a year traveling through open space with far less protection than we have here at home. A shifting boundary means a shifting radiation environment, and right now, most of our long-term mission planning still assumes something closer to a fixed, predictable shield. Engineers designing the next generation of deep space habitats have to plan for worst-case radiation exposure years in advance. If the shield itself moves, the worst case might look very different than anyone currently expects. Consider a crewed Mars mission currently being planned for some time in the next 2 decades. That crew would spend roughly 6 to 9 months in transit each way, almost entirely outside the added protection of Earth's own magnetic field. Every radiation model used to design their spacecraft's shielding, their sleeping quarters, and their maximum allowable mission length is built on assumptions about how much cosmic radiation actually reaches that far out into the solar system. If the heliosphere really does expand and contract on a cycle tied to solar activity, then the radiation environment those astronauts fly through could be measurably different, depending on exactly when their mission launches relative to that cycle. That's not a minor engineering footnote. That's the kind of detail that can shift how thick a hull needs to be, or how long a safe mission window actually is. It also changes how scientists think about habitability much further out, past our own solar system entirely. Every star with planets around it likely has its own version of a heliosphere, its own bubble of stellar wind pushing back against the galaxy. If our own bubble breathes and shifts the way Voyager 2's data now suggests, then the same is almost certainly true for other stars, meaning the radiation environment around potentially habitable worlds elsewhere in the galaxy might be far less stable than earlier models assumed. There's also the matter of Voyager 2 itself, and the ticking clock attached to everything it's telling us. It is running out of power. Engineers have been shutting down individual instruments one by one for years now, carefully rationing whatever electricity the spacecraft's aging power source can still generate. Every instrument that gets switched off is a decision made with real weight behind it, because once it's off, it's very likely never coming back on again. Best current estimates give it perhaps a few more years before it goes silent for good, its last signal fading into the same interstellar dark it's been quietly studying. Which means this exact data, this strange, boundary-flexing, textbook-challenging data, might be one of the very last things Voyager 2 ever manages to tell us. We may not have another spacecraft positioned this far outside the solar system for decades to come. There are concepts on the drawing board for a dedicated interstellar probe, something purpose-built to study exactly this kind of boundary. But those missions are still years, possibly decades, away from launch, let alone from actually reaching the edge of the heliosphere themselves. Even under the most optimistic timelines being discussed today, a new dedicated probe likely wouldn't reach the Heliopause until sometime in the 2050s at the earliest. Which means, whatever Voyager 2 is showing us right now about how our solar system breathes, we may genuinely be the last generation to get a live reading of it for a very long time. That thought alone is worth sitting with for a second. A spacecraft, older than most of the people watching this, is quite possibly giving humanity its final direct look at this phenomenon for the rest of the century. NASA's team is now working carefully through the numbers, cross-referencing Voyager 2's cosmic ray spikes against solar activity records collected over the last 18 months. They're trying to determine whether the timing lines up with one specific, identifiable solar event, or whether this is part of a longer, slower breathing cycle that's never been measured directly before. If they can confirm the breathing heliosphere model with this data, it will be the first time in human history that we've directly measured our own solar system expanding and contracting from the outside looking in. Not modeled, not simulated on a supercomputer somewhere, measured directly by a probe that was never even designed to still be functioning this far into its mission. A probe built with technology that predates the personal computer, the mobile phone, and the internet itself, and yet is still out there doing real boundary-breaking science. And if this data holds up under further analysis, it won't just quietly rewrite a paragraph buried somewhere in an astronomy textbook. It will directly change how scientists plan every future mission built to survive and operate at the true shifting edge of where our sun's influence finally runs out. It's worth remembering, too, that this wouldn't be the first time Voyager has forced scientists to throw out an assumption they were confident about. When it first flew past Jupiter, nobody expected to find active volcanoes on one of its moons. That single discovery rewrote what we thought we knew about geological activity on small, icy worlds. Before that flyby, most scientists assumed small moons that far from the sun would be geologically dead, frozen, silent, unchanging. Voyager proved otherwise almost immediately. When it reached Uranus, its magnetometer recorded a magnetic field tilted almost sideways relative to the planet's spin, something so unusual that scientists spent years trying to confirm it wasn't simply an instrument error. It wasn't an error, it was real, and it forced an entire rethink of how planetary magnetic fields can form. At Neptune, it found the fastest winds ever recorded on any planet in the solar system, tearing through the atmosphere at speeds that still hold the record decades later. Time and again, this same aging spacecraft has shown up somewhere nobody expected it to still be working, and quietly handed back data that didn't match the prevailing theory. This latest signal from the edge of the heliosphere might be the biggest example yet. There's a strange kind of comfort in that pattern, too. Every time this machine has surprised us, humanity has ended up understanding its own neighborhood a little bit better than before. It also raises a question worth sitting with. If a machine built in the 1970s keeps stumbling onto discoveries this significant almost by accident, what might a dedicated, purpose-built mission to the same boundary eventually find, once we finally have the resources to send one? We built something in 1977 to answer one deceptively simple question. How far does our solar system actually extend before it stops being ours? 48 years later, that same machine is still out there, still working against every original expectation. And it just told us the honest answer was far more complicated than we ever assumed. The edge of everything we call home isn't a wall standing frozen in place. It's alive in its own slow, cosmic way, breathing in and out over timescales far longer than a single human lifetime. And for the very first time, thanks to a spacecraft that should have run out of power decades ago, we are only just now learning how to actually listen to it breathe. Every reading it sends back from here forward carries a little more weight than the last, simply because we know there's a limited number of readings still left to come. Every data point is one more piece of a boundary we've barely begun to map, sent from a machine running on borrowed time, moving further from home with every single second that passes. There is something quietly humbling about that. A project started before most of us were born is still expanding what we understand about our own solar system right now in real time. Somewhere in a control room, a team of engineers who weren't even born when Voyager 2 launched are now the ones responsible for keeping it alive, decoding signals sent by scientists who have long since retired, using software patched together across 5 decades of upgrades. That handoff, generation to generation, is its own quiet piece of this story. The mission has outlived the careers of the people who designed it, and it's now being carried forward by people who grew up reading about it in the same kind of video you're watching right now. It's a reminder that some of the biggest discoveries don't come from brand new billion-dollar missions. Sometimes they come from something old, something we almost forgot was still out there, quietly doing its job long after anyone expected it to stop. And somewhere out there, drifting through the dark, far beyond Pluto, Voyager 2 keeps sending its faint signal back toward Earth, carrying answers to questions we didn't even know we needed to ask yet. Every year it survives is a year we didn't think we'd get. Every reading it sends is a gift from a machine that has already outlived every reasonable expectation placed on it. And when it finally does fall silent, whenever that day comes, it won't be an ending in the way we usually think of one. It will simply keep drifting, carrying its golden record, long after the last signal has faded from our antennas. It will pass by other stars over the coming millennia, close enough in cosmic terms to be considered a near neighbor, though still separated by distances too vast for us to ever confirm what, if anything, notices it passing. None of us will be alive to know if anything out there ever does find it. But the questions this single mission has already answered, decades after anyone expected it to still be capable of answering anything, are more than most missions manage in their entire operational lifetime. And that's the real takeaway buried inside all of this data. It's not just about one spike in cosmic ray readings or one mismatch in plasma density between 2 aging spacecraft. It's about how much is still genuinely unknown, even about the boundary of our own cosmic backyard, and how a machine built with 1970s technology is still the only thing capable of going out and checking. For now, though, it's still talking, still working, still telling us that the edge of everything we know is stranger and more alive than we ever gave it credit for. If you want to understand exactly how close we actually are to losing contact with Voyager 2 for good, and what NASA's last-ditch plan looks like to try to keep it talking for as long as physically possible, that's exactly what the next video is going to cover. Subscribe so you don't miss it when it goes up. And before you go, drop a comment below and let me know what you think. Do you believe the heliosphere is currently expanding or shrinking? I'll be reading through the answers, and I'll pin the one I think makes the strongest case.